So after 12.3 left us with inscribed angles in those theorems and rules, we're going to add in 12.4, angle measurements and segment lengths. So another section is kind of heavy on your theorems, but again, if we just apply them in the right places, should be fine. That first question you don't really have to do, but I kind of put my answers there for it. If we solve that, should be solvable based on what we know already, but we're kind of using this to build our rules for this new section. So getting to that vocab, angles formed by intersecting lines have a special relationship to the related arcs formed when the lines intersect a circle, and we're going to see those relationships. First thing we're talking about is a secant. Secant we haven't seen yet. We've talked about chords, we've talked about tangents, but a secant intersects the circle at 2 points, kind of like a chord, but again, it's got to go through. AB would be your secant ray, so if I start here at A, continue through the circle in 2 points, and go through B, that would be a ray. AB would be a secant segment because I could just start at A, stop at B, and that's still going through the circle and intersecting at those 2 points without it just being a chord. So chord is the part of the secant, but again, the chord is the part that stays inside the circle. So we're going to be using that in a few theorems. The first one, 12.13, talks about, and difference between these two is basically inside versus outside. Measure of an angle formed by two lines that intersect inside a circle is half the sum of the measures of the intercepted arcs. So what that's talking about here, if I have two lines that intersect, again, these are both secants because they're passing through the circle. If I intercept arcs x and y here, if I add those together, divide by 2, that should get me angle 1. And this angle is not labeled either, but remember what we know about verticals. Those should be congruent. Angle 1 in this unlisted angle. So my theorem there, again, if I'm looking for the measure of one of those angles inside, it's half of the sum of those two arcs, x and y. And the difference there is if I have two lines that intersect outside the circle, it's still half, but this time it's half the difference of the measures of those arcs that it is intercepting. So there's a few different situations that this could work with. This first example is when you're using two secants and they intersect outside your circle. I can compare that to when they're intersecting inside the circle. That's when you use the sum. But now that I'm intersecting outside the circle, I have two arcs that it's still intercepting, x and y. And you can think of it basically as inside and outside arcs. Y would be your inside arc. X is outside. It's farther away from your angle. And the way I remember this rule is your angle that you're looking for outside that circle that it forms there, those two lines that are intersecting. The measure of that angle, angle 1, is going to be half of x minus y. And again, you can remember that as outside minus inside, bigger minus smaller, farther minus closer. But that relationship holds true if I change those a bit. So this other example is using a tangent in a secant. Same thing. Angle 1 is bigger minus smaller arc, x minus y. And if I use two tangents, it's the same thing. So this time we just have to make sure that x is this entire arc on the outside. Subtract y, this arc on the inside, that gives us, divide by 2, that gives us that angle. So again, try these questions before we get to them, but let's look at that practice question. So we were trying to find the value of x here in this first example. A little bit hard to see. It's not really a very dark copy, but again, to find that, since it's intersecting inside your circle, those two lines, x is going to be 1/2 of the sum, 46 plus 90. So make sure we add those together, divide by 2, we get x is 68. That second example, it looks like those are intersecting outside your circle, so now I have to set up that angle 20 degrees equals outside minus inside. So that's 20 equals, I said outside minus inside, but remember that's half. Half of the difference, 95 minus z. So again, I have 20 equals half of 95 minus z. I'm doing some of my algebra steps there, so multiply to get rid of the 1/2. Subtract 95 on both sides, divide out the negative, and we get z is 55. Same things that we're pretty much doing for those other two, so it really comes down to those two formulas. If I'm meeting outside again, it's still outside minus inside, divide by 2, but again, I start with the angle, so the angle is 70. That's half of the outer one, w, minus the inner one, 110. If I solve for that, again, multiply by 2, we get 140, add 110, we get 250. Moving on to that next couple examples. Again, it's got the setup on there right now, but see if you can solve out the rest of it. If we have the intersection outside, again, you're using the difference. So you always want to think, is it a sum or a difference? Difference since they're meeting outside. And if I use that angle, y is going to be 1/2 of 110 minus 30. and 110 minus 30 is 80. Take half of that, I should get 40 for y. And last one, we go back to going inside the circle, so I see those two lines intersect inside. So that angle again, 35, is going to be half of the sum, x plus 30. Set that equation up, multiply out the fraction, so I get rid of the 1/2. Subtract 30, and we get x is 40. So we can also use this, basically it's that same rule if we're using it in this next word problem. Again, go ahead and see if you can try it before we get there. But if I have this satellite, I don't know if I'm going to read through that whole thing, but yeah, we basically just have a satellite that is orbiting the Earth, or to assume so, I guess. The important part there is that we have two tangents going from that satellite to the edges of the Earth. We want to figure out the measure of the arc that is viewed from the satellite. So that'd be the near side of the Earth there. And we can label that as x. Again, it's not really labeled for you, but it's always nice to label with what you're trying to find. That would be your x that you're looking for. And if I'm labeling the other arc, basically we don't know the exact measurement, but we know if I have the whole circle is 360, if I take away that near arc, I get the part that's left. So this is the leftover 360 minus x. And we're really just using that outside rule. So I'm using the half the difference of the two arcs. Our angle that we're given, 17.5, that's half of, again, the bigger minus the smaller. So half of 360 minus x minus another x. Gotta make sure I combine the x's together. In this, you could either divide these by 2, or you could multiply to get rid of your fraction. I multiplied, subtract 360, divide by -2, and we get 162.5 for that x. So adding in a few more theorems with our next page, let's go to that. So special relationship between two intersecting chords, two intersecting secants, or a secant that intersects a tangent. This relationship allows you to find the length of the unknown segments. And basically it comes down to these three patterns that we can see. You're going to have a separate theorem for each, separate formula. And I'll go down to the cases where we use those. Again, first case is if I have two chord segments, or two chords, I guess. And if I look at those segments of the chords, so segment of one chord, the other segment, so A and B make up one chord, D and C make up the other. So if I multiply A times B, that should be equal to C times D. So the products of the chord segments are equal. If I split up one chord, multiply the pieces, that should be equal to the other chord split up, as long as we're multiplying again. And if I look to my next situation, it looks like I have two secants again. And for our second case, the products of the sequence and their outer segments are equal. The way we see that being used here in the formula, W plus X, that would be one entire secant. So W plus X is that whole segment here. And times the outside part, so times just the W, that should be equal to the same thing on the other secant. So Y plus Z is the whole secant, times the outside part, so that's times Y. So again, I take the whole thing, X plus W, or W plus X, multiply times the outside, that's equal to the whole thing for this segment, Z plus Y multiplied by the outside. So the way I remember that is basically whole times outside equals whole times outside. In our last situations where I have a tangent segment and a secant, not two secants, and for this case, we have to take the product of the secant and its outer segment. So kind of like what we did in the last rule, whole thing times the outside. But then if I use this tangent segment, there's no such thing as a whole part and an outside part. It's kind of all outside. So I use the square of the tangent. So I just do basically outside times outside. So a whole thing, again, is Z plus Y, or Y plus Z, I have that written, times the outside part, Y, should be equal to the tangent part squared. And we're going to use those rules. We just have to pick which one follows each situation. Try to color code it a little bit to basically remember which goes with which case. And again, try and get to these before we get to them, but trying these example problems now. We have our first two, and looks like we're using case 2. Or we don't really have to remember it as case 2, but we're using two secants. So since I have a whole part and an outside, we're using that rule. So whole whole secant segment is 8 plus 6. So I did 14 for the whole thing, times the outside is 6, equals the same thing in the other secant. So that's Y plus 7, or 7 plus Y, that's your whole segment. And then times the outside is 7. Let's make sure we distribute, solve for Y, and we get our answer of 5. We have our third case where I have a tangent segment and a secant, so that's again whole times outside equals the tangent part squared. So 16 plus 8, if I combine that whole piece, that's 24 times the outside of 8. That should be equal to z squared, and then we can use our algebra to solve for z. And we have a couple more practice ones on the back. Again, see if you can try those before we see it, but let's take a look. We have another whole and outside part that we can use. So using that rule, the whole segment is 20 plus 14 times the outside of 14. Set that equal to the other whole segment should be x and 16 put together. So 16 plus x, or x plus 16, either way. And times the outside part there would be times 16. So I combine this, I get 34 times the outside is 14. Make sure I distribute on the other part, so 16x plus 256. Use our algebra to solve for x, and we should get about 13.75. Actually, I think that's exact, 13.75. And we finally get to our first case. We haven't really seen this one as a practice yet, but remember, if I have two chord segments, if I find the product of their segments, they should be equal. So 3 times 7, set that equal to 6.5 times m, and that should be easy enough to just divide and solve for m. We get about 3.2. So again, make sure you have these notes down, bring these in with class, and we'll check on those when we get there.